Okay, welcome to our probability and analysis webinar. And today we have with us Marcin Bownik from University of Oregon, who's going to talk about simultaneous dilations and translation tilings of Rn.
Okay, thanks, Paulina, for the invitation to speak. Yeah, it's hopefully this will be one of the last webinars or seminars on Zoom that I will have to give because, well, but it's still a nice way to, I would say, share the knowledge with the people that could be anywhere in the world. But I personally prefer to be doing in-person talks. So I would like to apologize in advance for maybe being clumsy in few places, but I mean, okay. So here is the title. Well, let's see. Here is the abstract of what I will be talking about. So in this talk, I will talk about wavelet cell existence problem, and maybe we don't have to read the whole abstract, but this is joint work with Darren Spiegel, who maybe is actually in the audience. Okay, so hopefully he'll correct if I say something correct. Okay, so what is a wavelet cell problem? So it's actually quite simple and elementary to state. So hopefully you'll get something out of this talk. So suppose you take an n by n invertible matrix, and you also take gamma a full rank lattice. You can think of gamma to be the standard lattice Zn. It really doesn't change the problem, but it's better to think of gamma as being arbitrary lattice. And now the question is the following: for what pairs of dilation and lattice does there exist a measurable set W that has two properties? So when you take the dilates of W by powers of A, these are integer powers of A, you get a measurable tiling of Rn. Measurable tiling means that you don't care about sets of measure 0. So the union of those AJWs is the whole Rn, and for different values of J, these are disjoint up to sets of measure 0. And then the second property is that when you start translating your set W by points of the lattice, you have measurable tiling of Rn. This is often called fundamental domain. So those two things have to be satisfied. Whenever they're satisfied, you have a wavelet set. Okay, so maybe some of you may not have seen what is a wavelet set before. So let's start from some easy one-dimensional examples. Really, the easiest example is this when you take dilation, which is 2, and we are in one dimension, the lattice is just integers. And this is the set W, just union of two intervals from -1 to -0.5 and 1/2 to 1. So now if you translate this by integers, you can see that, yeah, somehow, well, you take this interval from -1 to -0.5, translate this by 1 to the right, you get actually interval from 0 to 1/2. So you get, okay, you can see that they match somehow. When you translate the integers, you have partition of the real line. On the other hand, when you take dilates, you also have partition because this is like dyadic intervals. Okay, if you want to see a more complicated example, you can change the dilation factor to arbitrary number bigger than 1 and take the union of 3 intervals. There is one interval on the left of 0, and there are 2 intervals on the right, because that's essentially the minimal amount of intervals that you need to take for general A. That L here is 1 over the, I mean, the ceiling of 1 minus A minus 1. Well, you need to make some kind of calculations, maybe not immediate, I mean, but it's just elementary calculations that will show you that when you take dilates of the set W, so the other way to say this, when you take this trajectory of psi under powers of A, you take this characteristic function, this adds up to 1. And then when you take characteristic function of W and translate by integers, you also get 1. So that's rather elementary, but okay. Okay, so let's see. So now you can ask yourself about tilings of dilations, because tilings by translations, they always exist, regardless of what lattice you take. The tilings by dilation, there is this result that's quite elementary, but this is the first instance that we know that it has appeared in the literature, result of Larsen, Schultz, Taylor, and Spiegel. When you start from invertible matrix, then you want to find a set that tiles by dilation. This will only happen, you can find such set if and only if A is not orthogonal matrix. Okay, so often we want to have a set of finite measures. So there exists a set of finite measures that tiles by dilations if and only if the determinant of A is not equal to 1, in absolute value. And finally, if you want to have in addition a tiling that's a bounded set, then your matrix A has to be expansive, or it's inversely expansive. What it means is that when you look at all eigenvalues, real complex of A, they have modulus which is larger, strictly larger than 1. Right? So that's, well, maybe not everyone have seen this result before, but it's quite elementary to prove using the general normal form of the matrix. Okay, so now what is the motivation for the problem? The motivation comes basically from wavelet theory, because once you have a wavelet set, you can consider a function psi whose Fourier transform is characteristic function of a set W. So there is this check to inverse Fourier transform. This is a wavelet. So what it means is that when you take dilates and translates of your function psi, so translate by the lattice gamma star. Gamma star is a dual lattice because we are now in time domain. You take dilates by powers of B. B is the transpose of A because that's how the action of the Fourier transform. Okay, so then this is normalizing factor. This is an orthogonal basis for L2 of Rn. Right. So once you have a wavelet set, you have a wavelet. This is called MSF wavelet, minimally supported frequency wavelet. What it means is that those wavelets have the smallest possible support in the frequency. And that support is basically equal to the measure of the fundamental domain. You cannot have smaller supports. Well, the measure of support cannot be smaller. Now, the conjecture that's still open is once there exists a orthogonal wavelet set, does there exist a wavelet set? So that's what we don't know. This is like an annoying problem that no one was able to solve. Now we can more or less conjecture that simply this is true. I mean, it would be very strange if it wasn't. Now there is a very, again, annoying question that we don't know. It's due to Larson, that's I think now quarter-century old. That basically can be formulated like this: are minimally supported frequency wavelets minimal with respect to inclusion relation of frequency supports? So are those MSF wavelets really minimal? Because you have minimality in two ways. One, you look at the measure of the support in the frequency, it's the smallest, that's the definition. Or the other one, when you have two wavelets, you look at the supports of the Fourier transform, and one is smaller if the supports are included in the other. So I mean, so basically we are asking, once you have a wavelet, can you, in its support in the frequency, can you fit a wavelet set inside? And that's an open problem. I mean, for some reason, it's such a simple to state problem, but we don't know how to solve it. The other motivation comes actually, and this may not be that well-known problem, but it's still a classical problem, a Steinhaus tiling problem. So what this problem is about, you take a SON, so just special orthogonal group, and you take a standard lattice, but you just rotate it by. So this is just rotation of integer lattice. And now the Steinhaus tiling problem asks for the following problem: does there exist a single Lebesgue measurable set E such that this set is fundamental region for each of those lattices simultaneously for all the possible rotations? So now using Fourier transform methods called Tsakis and Wolf in 1999, they have shown that this is false in dimension 3 and higher. But this is sort of unusual. This problem is actually still open in dimension 2. So I mean, that's somehow strange. I mean, why normally when you have those type of problems like Akea problems, anything that's somehow non-trivial in Euclidean Fourier analysis, those things are non-trivial in higher dimensions, and dimension 2 is fully understood, but not here. And there is this very surprising result of Jackson and Moldin from 2002 that there actually exists non-measurable Steinhaus tiling of R2. Right, and this is a bit hard to imagine. How can you think of the set in the plane so that no matter what isometric copy of the integer lattice you take, it will meet exactly 1 point, every isometric copy of a lattice? That's the other way of reformulating of the Steinhaus problem. Okay, so what is that connection, commonality between Steinhaus and wavelet problems? That we have multiple actions of Rn for which it's easy to see that there are measurable tilings when considered separately. Not a problem to find a tiling for each of those lattices in Steinhaus problems, but yet it is not at all clear when and whether there is a single measurable set which tiles by both actions simultaneously. So that's the motivation. So now what are the prior results? So the first results from 1997 to Dilation and Spiegel, the wavelet set exists whenever A is expansive. So all real and complex eigenvalues are strictly bigger than 1, and gamma could be any lattice. Now, this results of Larson, Schultz, and Taylor about dilation tiling essentially says that determinant of A not equal to 1 is a necessary condition for existence of a wavelet set. And now, result that is due to myself and Lambing from 2017. When you start from any dilation that's not equal to 1, then for a random choice of lattice gamma, almost surely this will be there will exist a gamma wavelet set. So the dilation could be anything. You choose randomly lattice in the. So there is some kind of quality measure in the space of unimodular lattices, and that's the sense in which we talk about almost every lattice. Yeah, there will exist a wavelet set. So now comes the problem. This is really, I would say, breakthrough. At least something that's characterization in 2 dimensions that's due to lonescu and Wang. They formulated this result in a slightly different way than here, but this is essentially what they have proven, is that when you have a 2x2 matrix that has, let's say, for simplicity, determinant of A is bigger than 1, because it's less than 1, you take its inverse and not a problem. Gamma is a full rank lattice in R2. So now let's look at lambda 1 and lambda 2 eigenvalues of A. Suppose lambda 1 is bigger in absolute value than lambda 2. So there exists an A gamma wavelet set, if and only if the following happens. If the smaller eigenvalue is greater or equal than 1, then fine, there will be always exist a wavelet set. However, when the smaller eigenvalue is strictly less than 1, then what you do is the following. If you look at a contracting space, so the eigenspace corresponding to this eigenvalue less than 1, and this cannot intersect a lattice, right? So that, well, except at the 0, because that's where. So there is no non-trivial intersection for lattice. Okay, so let me explain more or less how this, by an example, what this example says. So I'll give you. So this is the same result. So let's take lattice gamma equals Z2, and let's choose the following dilations. So those dilations have 2 eigenvalues, 3, which is bigger than 1, and 1/2, which is less than 1. The determinant is 3/2, so it is expanding in volume. But now let's put some non-zero entry, let's say at this lower left corner. So now when you do this and you look what is the eigenspace corresponding to 1/2, you actually get, so you like subtract 1/2 from diagonal, you actually get the space spanned by E2, by second vector, like, so this is like a vertical line, right? And then this vertical line contains points in the lattice. Okay, so regardless what is alpha. Okay, so that's why you have non-existent result. But when you move this alpha to the other corner, situation changes dramatically. So when alpha is rational, there will be no wavelet set. Why is that? Because now when you look at what is the eigenspace corresponding to 1/2, it's actually a line with certain slope. If this slope is rational, then you will contain infinitely many points in the integer lattice. So there will be no wavelet set. But if this line has irrational slope, then it will miss all the integer lattice points, and then this condition is satisfied, and the wavelet set exists. Right? So I mean, so there's this delicate thing happening here between rational and irrational things. Okay, so now let's move to higher dimensions. So I would like to restate, because our goal is to somehow extend this lonescu-Wang result to higher dimensions. So how can we do this? Possible restatements in high dimensions when the smallest eigenvalue of A is less than 1 in modulus, because that's what we are really interested in. Some eigenvalues are less than 1. So actually you can prove the following things. The following things are equivalent dimensions in dimension n equal 2 when determinant of A is bigger than 1. Okay, so what are those conditions? So the first condition is like this. You take a ball of radius r. Radius is really not that important. You look at its negative dilates by A, and you intersect this with the lattice, and you see how many lattice points are there. So if this number of these lattice points is equal to 1 for infinitely many j negative dilates, then this is that condition. So Okay. The other possibility is that you look at the same dilates, negative dilates intersecting the lattice, and you want to know that this stays bounded, at least for some subsequence of J, not for all J, but lim inf as J goes to infinity. So for some subsequence, this is bounded by a constant. The other way to do this is to look at lattice subspaces. So you take any sublattice, look at the space spanned by that, it has dimension D. Again, look at negative dilates, but then this time intersect with that that subspace spanned by sublattice, and you look at the Lebesgue measure, and you require, for example, that those measures, D-dimensional Lebesgue measures, stay bounded, at least for some subsequence. So lim inf stays bounded. Or maybe the fourth condition, the space spanned by the eigenvectors associated with the eigenvalues less than 1 in modulus has a zero intersection, I mean trivial intersection. That looks the closest to the lonescu-Wang characterization. You have this 1, 2, 3, 4 characterization. They are actually equivalent in dimension 2. In higher dimensions, you have implications. 1 is the strongest, implies 2, implies 3, implies 4. 1 is sufficient. That was known. 4 is necessary because that's what lonescu-Wang showed. But which of this is really characterization? Actually, I mean, none of this. That's the difficulty. That's why this problem was so elusive for us. It's not so easy to figure out what is that, what is this characterization. So we are actually quite lucky, or maybe surprised, that we finally got this. We finally got characterization, and that's the result. It's a very simple condition that actually characterizes. So when you have a matrix with determinant bigger than 1 and full rank lattice, there exists a wavelet set if and only if. Okay, you look at the number of lattice points of negative dilates of a ball, but you put them in the denominator, so it's 1 over that. So that series must be divergent, right? And that's a characterization. Okay, so let's just think whether this makes sense with the prior results. So if A is expansive, so if A has all eigenvalues bigger than 1, then when you take negative dilates, basically the ball will get shrink because it's the inverse of a negative expansive dilation would actually shrink. So eventually it will lie in a ball, arbitrary full radius. Okay, so this intersection will have only intersect with an origin. So this denominator will be equal to 1. So you have just series of 1s, of course, diverges. Okay, so the wavelet set exists. Now, if you know that, let's look at this condition too. If you know this lim inf of this number of lattice points stays bounded, at least for infinitely many J, this means that the denominator is actually less than some number for infinitely many J. So actually this fraction is greater or equal than some epsilon for infinitely many J. Of course, so the series diverges. This is like n-term test that we teach people in calculus. That's in calculus. And finally, the third condition is maybe less trivial, but it's necessary. You can deduce this. I will tell. This is about the measure of this intersection with the lattice subspace. Okay, so now this is basically it. And so now how to prove it? I mean, so the proof of this is not so easy because essentially you have two different parts: sufficiency and necessity. In analysis, it's not often, doesn't happen often when you have characterization where you have really sharp. I mean, like we tell you when something happens, when something doesn't happen. So here, sufficiency, that's probably, let's start from this. First, I would like to define what it means for the set to pack redundantly or M redundantly. This means that when you take a dilate of that set, every point will recover at least M times. So this is the other way to say this. I mean, you look at the set U, look at the trajectory of AJ, of X under powers of A. This has to be bounded. When M equals 1, then this means that it packs by dilations. That's like different powers of dilations are disjoint. Now, covers is the opposite. So you have opposite inequality. And now the set tiles if it both packs and covers. And then that's what we say it's measurable tiling. So we have equality here. You can say the same thing about packing by translations or tiling by translations and covering. I mean, that's just the same concept. So now I'll start from elementary lemma, which is actually not too difficult to prove. So that this is the condition that is characterization. So the actual characterization was actually ball of radius 1, but it really doesn't matter what radius you take. If it's true for every r, it's true for some r, and the series diverges. But it's also equivalent to this condition that there is a sequence mj, so that reciprocals of that series of the sequence diverge, and but the set a to the power negative j b0 r, so negative dilate of a ball of radius r, packs mj redundantly via GABA translation for every j. Okay, so that's what we have. Okay, so now what is the key lemma for sufficiency? So it's a little bit dense. I'm not sure if we'll be able to. Okay, but let's attempt to understand it, because even each time I look at this lemma, it takes me a while to figure out what it actually says. So you start from invertible n by n matrix and full rank lattice. You have a set that packs by dilation. That's the set W. So it doesn't have to tell you by dilation, it just packs. Once it packs, you can define this dilation equivalency mapping, where you just basically project onto set W. You look at different, when you have set V, look at different powers of A, J, V, and you map them, intersect with W, you basically map them into W. So, okay, so this is this mapping DV. So now let's take U be a finite measure subset, and suppose we have this condition, that sufficient condition that one top is sufficient, that we have the sequence of nj of positive integers, so that reciprocals equals infinity, and a to the power negative ju packs mj redundantly via translation for every j. Then we can essentially somehow modify that set U that we had into another set. So, and we can do this for every epsilon. So for every epsilon, we can find set D, so that the set D packs by dilations the same. Okay, it will also pack by translations, but it will be dilation equivalent to U that you were. But moreover, it will have a very small Lebesgue measure, and that somehow enables you to play the game where you try to achieve at the same dilation tiling and translation tiling. In fact, there is another result which I didn't put a slide. It's only enough to, I think, have packing by translation and tiling by dilation. So it's not really, and then Cantor-Schroeder result will give you that. But okay, so this is the lemma. So now the base sufficient result will be like this: when you have, suppose you have a set W that tiles by dilation, but you have also partition of this set W into sets, and you have also this sufficient condition. So we have the sequence of positive integers that reciprocals diverges, and they A to the power negative JWM packs MJ redundantly via translation for every J. Then we show that there is an A gamma wavelet set. So this is actually that. I will not be saying exactly what is in that proof, but you have to use that lemma multiple times, and it's like inductive procedure where you each time you produce something that's closer to a wavelet set, but not in the limit, and in the limit you get a wavelet set. But it's quite elaborate procedure. I mean, now, how do you see now sufficiency? Okay, so why this condition that you have here is sufficient? Because this implies, first of all, existence of this MJ, that 1 over MJ equals infinity, and then they pack redundantly every ball of any arbitrary radius. So now when you take a set that tiles by dilation, I want to find this double partition of that, but it's just enough to take, like, it doesn't really matter. Like, take a ball of radius 0 to m, subtract the ball of radius. So it's like you take annulus. So this will also fulfill the assumptions of the above theorem, because every ball of radius r, this fulfills this assumption. So consequently, by that theorem, you have a existence of a wavelet set. Okay, so that's how much I wanted to torture you with the sufficiency result. I mean, well, let's go to necessity. For necessity, I mean, I don't know how much you have background in geometry of numbers, but this is a result that I really love, geometry of numbers. Because that's basically what we want to do, what the subject is about. You want to count the number of lattice points in convex bodies. The famous Gauss problem, when you have a ball of radius r, you want to know how many lattice points are in in that ball of radius r. Of course, it's proportional of the volume, but what is the error term? Stuff like that. In our case, will be our convex sets will be actually convex bodies, so they have non-empty interior. They're also symmetric. And when you want to see how many lattice points are there, then you have actually always automatic bound from below. The number of lattice points is at least equal to the measure, Lebesgue measure of that symmetric convex body, and you divide this by the volume of the fundamental domain. So it's Rn over gamma. And there is this factor to the power n. Okay, so that's what you have. But then there is converse to this, but you need to assume this convex body contains enough lattice points. So when you take linear span of those intersections with the lattice, that's equal to Rn. Then you actually have bound from above. There is another constant appearing here, which is maybe ugly, to the power n times n factorial. But other than that, you have also bound from above. And that's really beautiful result. I mean, that enables us to, it's a quite standard result, actually. It enables us to prove necessity. So the key lemma for necessity is like this. It's probably easier than for sufficiency. So hopefully you'll be able to understand this. So if you have invertible matrix and full rank lattice, you take a measurable set that packs by gamma translations. So there is no mention about dilations, just set that packs by gamma translations. Then there is a constant C, which depends on the dimension, universal constant. So that when you take a ball of radius 1, centered anywhere, and see how much it contains of that set AW, right? So then this is somehow, the Lebesgue measure of this is bounded, it's controlled by the number of lattice points in the A inverse. So you take the unit ball, take its inverse under your dilation A, and you look at how many lattice points are there. So if this is large, this volume has to be somehow small, right? I mean, that's I would say what we have. It's elementary result. It's about okay. Basically, using the previous lemma that I showed you, you can prove it. And now there is this. We want to show somehow non-existence of results of wavelet sets. So this is a result due to Spiegel that it's quite elementary, and this was the only known result that shows non-existence of wavelet set. It's quite easy to show. I will not show you the proof, but it turned out to be also sufficient for getting this characterization. So you start from a set W, and this is like a candidate for the wavelet set. You wish that, okay, but now suppose that there exists epsilon and dilation generator U that contains infinitely many disjoint sets VK of measure at least epsilon. And then what you do is the following. You look at each of those disjoint sets VK, you look how much they intersect with positive powers of the dilations of the set W, and you look at tail of that. So sum of J goes from capital J to infinity, and you take the limit as J goes to infinity. But before you take the limit, you take supreme over K. So if that supreme over K goes to 0, so this sum like uniformly goes to 0, then W cannot be a wavelet set. It's actually not too difficult to prove it, because once you have a wavelet set, you actually prove that this supremum has to go to, well, it has to go to, I guess, 1, well, or the measure of decay. It has to go be at least epsilon. And so it's not too difficult to prove this proposition. Okay, so now how do we show necessity? I'll try to argue. So now explain to you, because it's actually not too difficult. So once you have those pieces, so suppose that that series converges. So convergence of the series, if this is characterization, would have to imply that there is no wavelet set. Okay, so let's take a W set, that measurable set that tiles by translations. We want to show that it will not tile by dilations. So now you can find a dilation tiling generator that contains a collection of disjoint balls, let's say VK, each having the same radius, let's say less than 1, let's say equal, I should probably say equal to 1 for simplicity. Let xk denote the center of decay. Then we have this key lemma 2. When you intersect ball with the image of that set W under, because W was a tiling set, fundamental domain, AJW, then applying that lemma, this is bounded by the number of the lattice points in the negative. Here you have you take the inverse of AJ. Okay, so now by this condition 3, you know that this series converges. So when you look at the tail of that series, it just goes to 0, right? I mean, so these are positive terms. So then that series VK intersecting with the AJW actually goes to 0 regardless of what is K. So so this implies that W is not a wavelet set by the proposition that we had here, right? This was the proposition AJ goes to 0, so it cannot be a wavelet set. So exactly. So we have shown that there, if this condition is satisfied, there will be no wavelet set. And this is pretty much how the proof works. At least that's how I wanted to say. So now there is another convenient necessary condition that we had for a while, but it's actually easier to check. And this is the condition, I think, 3 in the when I had that list of equivalent conditions in dimension 2. So when you have invertible matrix determinant A bigger than 1 and you have full rank lattice, suppose you have this condition, you look at negative dilates of your unit ball, but then you intersect with any lattice subspace, so space spanned by sublattice lambda. This is d-dimensional space. You look at Lebesgue measure. If this Lebesgue measure goes to infinity, then there will be no A gamma wavelet sets. Right. So that's what we can prove. Okay. So now, what are the applications of this result? So the first application is actually a little modest, I would say, generalization of the result of Dye, Larson, and Spiegel about existence of wavelets for expanding dilations. But we have to use quite a non-trivial result of Margulis. So what does it mean that matrix is unipotent if all of its eigenvalues are actually equal to 1? What Margulis have shown is the following. When you take a full rank lattice gamma in Rn, and you have a 1-parameter group of unipotent matrices, then you can find delta small enough, I would say, radius, so that your ball of radius delta will miss the image of your lattice under the action of this 1-parameter group of dilation, well, except at trivial points, because for infinitely many t, well, not for t, not only for t, I mean for infinitely large t. In fact, there are even better generalization of this result, that like density of that set T where this misses is actually positive. So I mean, yeah, for a substantial number of you will miss it. And this is exactly what we need here, because once for this result, so well, it's not completely trivial to prove it, but okay. But once you have a dilation that's expanding in volume and all eigenvalues are greater or equal to 1, so yeah, allow our eigenvalues to be equal to 1, then actually what will happen for every full rank lattice gamma, there exists a gamma wavelet set. And the reason for this is that when you look at the balls, ball of radius 1, it will contain like infinitely many dilates of that ball, negative dilates, will contain a bounded number of lattice points. So that series that this characterization will actually, well, okay. So what I wanted to say is that, let me just come back to, yeah, that this condition will be satisfied. Condition 2. Okay, so let's come back to that. So this is just a generalization of, I went a bit too far. This is a generalization of a result of Dye, Larson, and Spiegel. By tiny bit, we just allow, you can allow your eigenvalues to be equal to 1, and you are okay. Your wavelet set exists. But well, the proof is non-existent, not trivial. But what is also true about this result? This result is actually optimal. There are no this actually classify all dilations for which you have a wavelet set for every full rank lattice. as soon as one eigenvalue is below one, then there will be lattices for which the wavelet sets do not exist. In fact, we have the following generalization of result of lonescu and Wang. Okay, so let's consider diagonal matrix for simplicity. You arrange eigenvalues in decreasing order. They are all strictly bigger than one, but the last one, this loner, is below one. And suppose this loner is really, I mean, not very harmful. I mean, in the sense that when you multiply this eigenvalue, which is less than one, by the next one, which is bigger than one, you have expansiveness. So you have expansiveness in every two-dimensional subspace, essentially, in terms of at least volume or area. That's what it really says, I mean, geometrically. So now if you take a full rank lattice, there exists a wavelet set if and only if, well, this contracting space, En, because this is the eigenspace corresponding to this contracting eigenvalue lambda n, this eigenspace cannot meet with your lattice. If it doesn't meet, then the wavelet set exists. If it meets, that it doesn't exist. So it's exactly lonescu-Wang result in dimension n equal 2. So that's the best, essentially, how you can do, because this condition is really not sufficient. Why is it not sufficient? I have example that's maybe a little bit hard to again maybe follow, but it's a 3D example. You have again diagonal matrix with eigenvalues lambda 1, lambda 2, lambda 3. Put them in decreasing order. In terms of volume, your dilation is expanding, but while lambda 3 is really quite below 1, in the sense that when you multiply by the largest eigenvalue, it's still below 1. So now I claim that there exists, we claim what we can show that there exists gamma, not we claim, we assume that there exists gamma 1 and gamma 2 points in the lattice, so that when you span, look at the span by those 2 points in the lattice, it actually, you get a Bownik space. It will contain eigenspace E3 corresponding to this eigenvalue lambda 3, but then you have this kind of non-trivial vector, which is linear combination of E1 and E2. So then you can show that there is no A gamma wavelet set. So what I wanted to say is that in this case, this condition that you have in the previous result is actually, like, this intersection could be trivial, but yet the wavelet set do not exist. So this is necessary, like, condition, this intersection that what happens for the eigenspace corresponding to contracting eigenvalues, but it's not sufficient by no means, and that's that example essentially shows. It's not too difficult to see this example using our characterization result. But, okay, so now the other example, maybe this is the last example I wanted to show. First, let me remind you result of Khinchin. It's a classical result in Diophantine approximation that tells you the following. Suppose you have psi j, function that goes to 0 of arbitrary fast. Then what Khinchin showed is that you can find numbers alpha, beta, which are very far from being algebraic. I mean, they have to be transcendental. So that for such a large j, you can always find integer solution A alpha plus B beta equals 1, but it's not exactly not equal to 0, but it's almost like the norm of this is equal almost to 0. So it's bounded by this psi j. This function psi j goes arbitrarily fast to 0, as I mentioned. And those solutions correspond to small value of A and B, because eventually you get a solution, but here you have solution that happens really, I mean, right. So those numbers, those A alpha beta they have to be irrational, but they have to be irrational, but then their linear combinations are very well approximated rational numbers. Okay, so this norm is actually denotes the distance to the nearest integer. Right, so that's maybe what I should have said. Okay, so now another 3D example, and maybe the last one that I wanted to show you is the following. This volume condition is really not a right way of characterizing, because you can find a lattice gamma in R3 invertible diagonal matrix A with determinant A bigger than 1, so that no A gamma wavelet etc. exists, despite the fact that for every subset of F, so when you look at V, this is the span of F, so you look at the lattice subspace and see what is the dimension of the intersection of this lattice with negative dilation. Suppose, yeah, this goes to 0, but yet the wavelet set doesn't exist. And you can even specify, I can even tell you exactly how this dilation looks. So it's 10, 1/2, 1/2. This is expanding in volume because the determinant of this is 10 over 4. Yeah, that's, you take numbers alpha, beta association theorem for Psi that goes pretty fast to 0, like 11 to the power negative j. Then this is the your lattice 1, 0, 0, alpha 1, 0, and beta 0, 1. And then one can show that somehow those volumes actually go to 0, but yet the wavelet set will not exist. It will not exist because when you look at the number of lattice points in the negative dilates of that of the unit ball under this dilation, under this matrix, you get this, and look at reciprocals, you get summable series, and that's what will happening. So, well, it's close to 11:45, so I think end here. So, thanks for your attention.
Thank you. I'm going to pause the recording.